Hello everyone, my name is Juliana Rojas and I am a master student in materials engineering at the University of Antioquia, Colombia, and I am a representative of CDMAS group. I'm going to talk about my research development of a high entropy titanium zirconium hafnium molybdenum ion alloy by mechanical alloying. I would like to begin by speaking about conventional alloys and then I will move on to biohigh entropy alloys. Between the conventional alloys, we have commercially poor titanium and titanium aluminum vanadium alloys, which have gained prominence in orthopedics and dental implants due to their excellent properties. However, titanium aluminum vanadium has some disadvantage. For example, its elastic modulus is higher than that of bone, leading to biomechanical incompatibility. Besides, its lower resistance can result in the release of metal particles under repetitive stress conditions, causing inflammation and damage to surrounding tissues. In addition, aluminum and vanadium elements present toxicological risk, including accumulating in vital organs such as the kidneys, liver, spleen, and brain, leading to negative health consequences. Ideally, implant materials should combine a high strength, low elastic modulus, high wear and corrosion resistance, and excellent biocompatibility. However, very few materials meet all these conditions. This suggests that it's difficult to find a material that provides optimal long-term performance without risk. For example, high-entropy alloys could be a good alternative. These materials are composed of 5 or more main elements with an atomic percentage between 5% and 35%. High entropy alloys in the biomedical materials field, called biohigh entropy alloys, are mainly composed of elements commonly found in biocompatible binary and ternary alloys such as titanium, zirconium, hafnium, molybdenum, tantalum, niobium, among others. Research on biohigh entropy alloys has grown quickly due to their high wear resistance, high corrosion resistance, and excellent biocompatibility, making them promising candidates for heat processes, artificial joints, and dental implants. Therefore, they could be a solution for the problems that conventional alloys can't address. For this reason, the objective of this research is to develop a new biohigh entropy alloys with the constituent elements titanium, zirconium, hafnium, molybdenum, and niobium using two different methods, high energy milling and induction melting. To carry out both processes, the metal powders, titanium, zirconium, molybdenum, and niobium, and hafnium were dosed in an equiatomic ratio of 20%. Then they were mixed manually. These powders have different morphologies, including irregular shapes and spherical agglomerators with particle size ranging from 11 to 44 micrometers. For milling process, the powder mixture was deposited into the pot in a relation bulk powders of 20:1. All this process was carried out in controlled atmospheric conditions to avoid oxidation. Subsequently, the milling process was performed for 30 hours at 500 rpm. It is important to mention that the idea is to evaluate how the different milling times could affect the crystal structure of the materials. For this reason, we took a small fraction of materials every 10 hours and evaluated them through X-ray diffraction. For induction melting process, the powder mixture was milled for 30 hours, then compacted to 500 megapascal using hydraulic press, forming cylindrical pellets. These pellets were deposited in a graphite crucible, which is efficiently heated by induction and transfer heat to the metal by conduction. Then the crucible containing the pellet was placed in the furnace cold to begin the induction melting process under vacuum conditions at a temperature of 2071 degrees. The image 1 shows all the result of X-ray diffraction of the alloy obtained by mechanical alloying and induction melting. The blue patterns shows all the peaks corresponding to the constituent elements of the alloy, such as titanium, zirconium, molybdenum, hafnium, and niobium. These peaks are sharper and have a higher intensity than the intensity of powders subjected to longer milling times. With the increase of milling times, not only does the relative intensity decrease, but the diffraction peaks also become broader. This behavior is attributed to the intense impact energy during mechanical alloying that causes a reduction in the size of the crystal. The magnified view of the X-ray diffraction pattern between 28 and 42 shows that increasing the milling times, most of the initial peaks disappear. The disappearance of these peaks suggests that some phases or components of the sample have been reduced, eliminated, or transformed into new phases. In addition, the disappearance of the diffraction peaks indicates the start of the formation of a solid solution phase. Now, I will focus on pin pattern corresponding to milling for 10 hours. These patterns shows that the low intensity peaks corresponding to titanium disappear due to that the elements with lower melting temperature tend to form a solid solution phase before those with higher melting temperature as a result of its higher diffusion capacity. After 20 and 30 hours of mechanical alloying, the peaks were indexed to three different phases: hexagonal compact structure and two-body cubic center structure, BCC1 and BCC2. The most intense peak is observed at 40.5 degrees with a preferential orientation in the 110 plane and is associated with the BCC1 phase rich in molybdenum. On the other hand, at angle 38.6 degrees, a BCC2 phase with an abundance of niobium is evident. After the combined process of milling and induction melting, peaks associated with BCC1, BCC2, and HEP phase were identified. In addition, low-intensity peaks associated with oxides and carbides of titanium and niobium are observed. The carbides were formed from the reaction between the metallic elements and the carbon from the graphite crucible used in the process. On the other hand, the higher intensity of the BCC2 peak suggests a large fraction of this phase compared to BCC1 and HEP phase. This indicates that during induction melting, the system reduced its total free energy, leading to the formation of a dominant BCC2 phase. The microstructure of biohigh entropy alloy after the induction melting process shows the dendritic and interdendritic regions. According to the EDE's analysis, the dendritic regions consist mainly of hafnium and zirconium. This is because they have the same crystal structure, equivalent covalent radio, and a similar lattice parameter, which promotes their segregation in the zones and the formation of the stable ACP phase. On the other hand, interdendritic regions is composed of titanium, niobium, and molybdenum in a significant atomic percentage. These elements have a lattice parameter close to the calculated lattice parameter of the BCC phase. We suggest that they could have acted as the host lattice for the BCC phase. The elemental mapping shows that titanium, zirconium, and hafnium are uniformly distributed across the sample. However, zirconium and hafnium exhibit microsegregation in the dendritic regions. On the other hand, molybdenum and niobium show clear segregation in interdendritic regions. On the other hand, the chemical composition results indicate a composition close to equiatomic. In conclusion, in this work, a titanium, zirconium, molybdenum, hafnium, niobium based high entropy alloy material has been developed through mechanical alloying and induction melting. After 30 hours of mechanical eloging, the melt powder consisted of three different phases: BCC1, BCC2, and HEP. The lattice parameter of the BCC phase are closely aligned with molybdenum, titanium, and niobium, while the lattice parameter of the HEP phase are aligned with those of zirconium and hafnium. During induction melting, the system minimizes its total free energy, leading to the formation of a dominant BCC2 phase, and the biohigh entropy alloy exhibits a dendritic macrostructure. Thanks for your attention.